In this problem, draw the shear force and bending moment diagram for the following beam. Here, this is the beam. Okay. Here you can see the pin supported at the A end, at the C end, rolling support. Here the distributed load, the 20 kilonewton per meter load is acting. The uniformly distributed load. Okay. When you are going to draw the shear force and bending moment diagram, you have to follow a set of these steps. As the first step, we have to determine the support reaction from the free body diagram of entire beam. Then, as the second step, divide the beam into segments so that the loading within each segment is continuous. Here you can see from A to B, the loading is continuous. The distributed load is continuous from A to B. From B to C, the loading is continuous. There's no load acting in the B2C region. So we have to divide this entire beam into two segments, A to B and the B to C. So we have to obtain the equations considering A to B region separately and the B to C segment separately. Okay, first of all, let's determine the support reactions. First of all, we have to draw the free body diagram for the entire beam. Okay, let me draw the beam. This is the beam. Here for the pin support, there's no any horizontal forces acting on it. So we can directly mark RA like this. Same as in here, RC. Okay. Here you can see the distributed load, the parallel forces acting throughout the region A to B. The total load acting on it is equal to 20 kilonewton per meter. That means if you take the meter length, the 20 kilonewton force is acting. Here it is acting throughout the length A to B. That means the 3 meters. So the total load acting is equal to 60 kilonewton. 60 kilonewton. Okay. This is the B point. This is the C point. So then the 60 kilonewton force we can represent by a resultant force of these parallel forces acting at the middle. Acting at the middle of the beam. 60 kilonewton. That is acting at the middle. Okay. So then what are the dimensions? Here 1.5 meters. Here again the 1.5. Here 1 meter. Here 1.5 meters. Okay. So then we can write the value for the RA. RA is equal 60 into, here the total length is equal to 4 into 2.5. Then the RC is equal 60 into 1.5 divided by 4. So then what are the answers for this one? Here that is equal 37.5 kilonewton. This one is equal 22.5 kilonewton. These are the support reactions. These are the support reactions. Okay. Then we are going to consider to obtain the equation for shear force and the bending moment. For we are going to divide the beam into segments A to B and B to C. So first of all, we are going to consider the A to B region. Okay, A to B region. Okay. So then, what is the next step? When drawing the shear force and bending moment diagram, introduce the imaginary cutting plane within the segment located at the distance x from the left hand side of the beam. Okay. So I'm going to introduce imaginary cut. Okay, somewhere in here. The x distance from the left hand side of the beam. Here, the distance is x. Okay. So then I'm going to consider this separated beam part. This one separately. So I'll draw this separated beam part. Okay. Then we have to mark all the forces acting on it. So what are the forces acting on it? At here it is at 37.5 kilonewton is acting. Then the distributed load is acting. The distributed load in this segment, the intensity of the distributed load is equal to 20 kilonewton per meter. The length of the segment is equal to x. Then we have to mark the shear force and bending moment. Shear force and bending moment. So according to the sign convention, we are going to mark the positive shear force as a downward direction, the shear force, and according to the positive sign convention of the bending moment, marking the bending moment as in this. Okay, these are all the forces acting on this beam segment. Okay, these are all the forces acting on this beam segment. So we are going to find, these are the unknowns. We are going to find shear force and bending moment by the variable of x. Okay. So by writing the equilibrium equations, we are going to find the equation for shear force and bending moment. Okay. So we are going to consider the vertical force balance of the beam. Okay. Consider the vertical force balance. So what are the vertical forces? 37.5, that is acting upward direction, minus here the distributed load, the 20 into x kilonewton downward direction. So again the minus the shear force is equal to 0. Okay, minus is equal to 0. Okay, then by making the shear force into subject, shear force is equal to minus 20x plus 37.5. This is the equation for the shear force. This is how shear force is vary throughout the length of the beam A to B. Throughout the length of the then again I am going to obtain the equation for the bending moment. Okay, to get the equation for the bending moment, I am going to take the moment around the A point. Okay, moment around the A point. By taking the moment around the A point, okay, then bending moment is acting. Then the moment produced by this distributed load, that is acting clockwise direction, minus x divided by 2, that is the lever arm, because the resultant of this distributed load acting at the middle of the, here I am drawing the resultant of this distributed load, that is equal to 20x, that is acting middle of the beam segment. This is the lever arm, that load acting is equal 20x. These are the only then from the shear force, minus shear force into x is equal to 0. Here the bending moment, by making the bending moment into subject, we are getting 10x square plus shear force into x. Then the bending moment is equal 10x square, the shear force plus 20x plus 37.5 into x. Bending moment is equal 10x square minus 20x square plus 37.5 into x. Finally the bending moment is equal minus 10x square plus 37.5 into x. So then we are going to separately consider the B2C region. B2C region. Okay, so I'm going to introduce the imaginary cut in between the B2C somewhere in here by taking the distance from left hand side x to the imaginary cutting plane. So let me draw the diagram. Here the load is equal 37.5. Then let me mark the shear force and the bending moment. Okay. Then these are all the forces acting on this beam segment. Okay, this distance is equal to x. This distance is equal to x. Okay, so then we are going to, similarly in previous, we are going to obtain the equation for the shear force and bending moment considering the equilibrium of this beam segment. Okay, 20 kilonewton per meter. So the resultant is equal, here it is acting 3 meters, 60 kilonewton. Okay, let's take the vertical force balance in upward direction. 37.5 kilonewton is acting. In the downward direction, minus 20 into 3 kilonewton is acting. Again in downward direction, the shear force is acting is equal to 0. Then directly we can obtain for the equation of the shear force, that is equal to minus 22.5 kilonewton. Then by taking the moment around this A point, again we are going to find the bending moment. Then here this distributed load, the resultant is acting at the middle, that is equal to 60 kilonewton. So minus 60 into the lever arm is equal to 1.5 meters. Then again the minus shear force into the distance, the lever arm is equal to x, plus bending moment is equal to 0. So then the bending moment is equal shear force into x plus 90. So the bending moment is equal, the shear force is equal minus 22.5 into x plus 90. This is the equation for the shear force and the bending moment for the beam segment B2C. Okay, now we can draw the shear force and bending moment diagram. Okay, let's see how to draw the shear force and bending moment diagram. Okay, in this problem, now we are ready to draw the shear force and bending moment diagram. We have already obtained the shear force and bending moment equations. Okay, for A to B region, the obtained shear force from A to B region, the obtained shear force is equal, shear force equation is equal minus 20x plus 37.5 kilonewton. Then the shear force x is equal to 0. The value is equal 37.5 kilonewton. At x is equal 0, the value is equal 37.5 kilonewton. Then the shear force x is equal 3 at B point. The shear force value is equal, by substituting the value in 3 here, is minus 60 plus 37.5, that is equal to minus 22.5 kilonewton. Okay, it's a linear equation, negative gradient linear equation, so we can simply draw that one. Okay, again we have to mark another thing, the shear force equal to 0. So we are going to find where the shear force curve is intersecting the x-axis. So that is equal to minus 20x plus 37.5, so that x is equal 1.8 1.875 at x is equal 1.875. It intersect x-axis, so that first of all we have to mark that one also. So main here, so then you can easily draw that one. Yeah. We have to give rough proportion for this. This value is equal yeah, 37.5 kilonewton. This value is equal minus 22.5 kilonewton. Okay. Okay. So then that is the shear force equation. The bending moment equation for this region is equal to the bending moment equation we obtain, that is equal to minus 10x square plus 37.5 into x. Then the bending moment x equal to 0, the value is equal to 0. By substituting the 0 in this equation, we can easily calculate bending moment at x is equal 3. So that means at this B point, we are going to find the bending moment. What is the value? By substituting 3 in this equation, we can easily calculate that one. I have already calculated that value. That is equal 22.5 kilonewton meter moment acting on this cross section of the beam. Okay, then here you can see the quadratic equation having the maximum. Where it is maximum? So where it is maximum, we can easily calculate d by taking the derivation. D bending moment with respect to dx is equal minus 20 into x plus 37.5, so that x is equal 1.875 at the bending moment is maximized. So then we have to find the maximum bending moment value. The bending moment x is equal 1.875. The value we have to calculate by substituting this value in this equation, minus 10 into 1.875 into square plus 37.5 into 1.875. The value is equal 35.156 kilonewton meter torque. Moment is apply on the cross section at the B. Then again we have to calculate the bending moment at x is equal 3. We have to calculate the bending moment at x is equal 3. By substituting this 3 in this equation, we have to calculate that one. The minus 10 into 9 plus 37.5 into 3, that value is equal 22.5 kilonewton meter torque is applied. Okay, so then now we are ready to draw the bending moment equation for this A to B region. First of all, we have to mark these points. At x is equal 0, the value is equal to 0. So then x is equal 3, the 22.5, and the at x is equal 1.875, that is the maximum value is 35. Let's draw the roughly. Let's take the value for this. You all know as the shear force curve, we are getting the derivation of bending moment curve, so that at this point the bending moment should be maximized. So the maximum point we are marking just below this intersection point of the shear force curve, because at the maximum its derivative is equal to 0, so that the shear force goes to 0 at this point. So then this point is equal to 35.156. That value is equal to 35 point sorry 156 kilonewton meter moment be the point. So then at x is equal 3, 22.5. Some man here. Okay, then now we can do the curve. This parabola. The parabola. Okay, this is the curve for the bending moment curve for the A to B region. Okay, now let's move to the next region, the B2C region. Okay, B2C region. In B2C region, if we take the B2C region, the shear force equation is equal minus 22.5 kilonewton, the constant value. So then you can easily draw that one, constant value. Then it goes to 0 at this free end. Okay, this is the shear force curve. This is the complete shear force curve. Okay, then what is the bending moment? Okay, let's draw the bending moment also. The bending moment for this B2C region, the bending moment is equal, bending moment equation is equal, bending moment equation is equal minus 22.5 into x plus 90. Then the bending moment x is equal 3, the value is equal 22.5. Then bending moment x is equal 4, that value is equal to 0. Here is a linear equation having the negative gradient, so that we can easily draw this curve by joining the 2 points. 3 is same as this point coinciding, so then it goes to 0. This is the bending moment curve. Okay, this is how we are drawing this shear force and bending moment diagram for this kind of beam example. Okay, thank you for all.